Hi, I wanted to go over the quiz that you took yesterday since there were some issues, particularly with the front half of the quiz. So let's take a look. The first thing we're given on the top of the quiz are Ka values for 5 different weak acids. And question number 1 says, write the equilibrium reaction for a buffer solution with a pH of 2.5. So there's a couple things that we need to think about in order to answer this question. First of all, we need to know what a buffer solution is. So a buffer solution is made up of a weak acid and a salt of its conjugate base, or a weak base and a salt of its conjugate acid. And it's in equilibrium, and it will resist changes in pH as long as we're within the buffer capacity. The other thing we have to know in order to answer question number 1 is that when we're selecting a buffer solution, we want the pKa value to be as close to the pH value as possible. So we want to make a buffer solution with a pH of 2.5. And if we look at the choices for our weak acids, hydrogen sulfate has a pKa value of around 2. Hydrogen sulfite has a pKa value around 7. Dihydrogen phosphate has a pKa value around 8. Hydrogen carbonate has a pKa value around 11. And hydrogen phosphate has a pKa value around 13. And all I'm doing is taking the negative log of the Ka to come up with the pKa value. So if I want a pH of 2.5, the hydrogen sulfate ion is going to be my best choice. So the buffer solution is going to be made with a salt of hydrogen sulfate and a salt of sulfate ions in solution. And we want to calculate what the mole ratio of that base to acid would be, and then what the gram ratio would be in order to make the solution. So when we look at question number 2, it says if you have only 1 gram of the salts of each of the weak acids above, how quantitatively would you make 100 milliliters of this buffer solution? First of all, the volume of the solution isn't going to make any difference because the acid and the base are going to be in the same solution. So the ratio of the acid to the base is a constant no matter what the volume of the solution will be. So then I need to figure out what salts I'm going to use. If I want a buffer solution of hydrogen sulfate ions and sulfate ions, I can't just get those ions out of a container. They need to come from salts of those ions. So I'm going to pick a cation, usually an alkali metal, sodium or potassium, to make my salt. So I chose sodium. So I have sodium hydrogen sulfate and sodium sulfate as my 2 salts that I'm going to make my buffer solution out of. And I need to figure out how many grams of each I would add to my solution to give me a pH of 2.5. So if my pH is 2.5, I want to find out what my hydrogen ion concentration is. So I'm going to take 10 to the negative pH, or 10 to the negative 2.5. So that'll give me 3.16 times 10 to the minus 3 for my hydrogen ion concentration. Next, I'm going to take my Ka expression, which is the products over the reactants. So my concentration of hydrogen ions times the concentration of my sulfate ions over the concentration of my hydrogen sulfate ions. I'm going to divide both sides by my hydrogen ion concentration, and I'm going to get Ka equals my hydrogen, or Ka over my hydrogen ion concentration will equal the concentration of my base over the concentration of my acid. Okay, so moving down a little bit, I calculated that my hydrogen ion concentration with a pH of 2.5 is 3.16 times 10 to the minus 3. The Ka value for hydrogen sulfate is 1.2 times 10 to the minus 2. And that ratio will give me the ratio of my base to my acid. So I'm going to take 3.16 times 10 to the minus 3 divided by 1.2 times 10 to the minus 2, and that's going to give me a 0.26 to 1 ratio. Now that's a concentration ratio. It's a concentration of my sulfate ion to my hydrogen sulfate ion in the solution. But it's also my mole ratio since both ions are going to be in the same solution and the volumes cancel out. So I'm going to use sodium sulfate and sodium hydrogen sulfate as my salts of my acid and my base. So sodium sulfate is the salt of my base in my buffer solution, which has a molar mass of 142.04 grams per mole. So I'm going to take 0.26 moles and convert that to grams, and I get 36.9 grams of sodium sulfate. I'm going to do the same thing with my sodium hydrogen sulfate, so my molar mass is 120.06 grams per mole. If I have 1 mole of that, that gives me about 120 grams of my sodium hydrogen sulfate. So if I took 36.9 grams of sodium sulfate and 120 grams of sodium hydrogen sulfate and added it to a solution until it all dissolved, my pH would be 2.5. But that is huge quantities of my salts, and I don't ever use that quantity of salts. And the question tells me I only have 1 gram of each salt. So if I were to divide both of those quantities by 120, that'll keep my ratio the same, but it'll give me 0.31 grams of sodium sulfate and 1 gram of sodium hydrogen sulfate. The ratio is still the same. The pH is still going to be the same. I'm just going to have less salt in my solution, which means my buffer capacity would be less. So if I were to take those 2 salts and add them to a quantity of water and get it to all dissolve, the pH of that solution would be 2.5. And then question number 3 says, does the amount of water added matter? And the answer to that would be no. And that's because my ratio of my base to acid is going to be the same whether I talk about molarities or I talk about moles, because they're both found in the same solution. Now let's look at the questions on the back where we're going to calculate the pH of a particular buffer solution and then add a strong base and a strong acid to that buffer solution. So question number 1 says calculate the pH of a solution that has 0.60 molar hydrogen or hydrofluoric acid and 1.00 molar potassium fluoride, and it gives me the Ka value. So the first thing I want to do is write my equation for the buffer solution, and since I know the Ka value for hydrofluoric acid is greater than the Kb value for fluoride, my equilibrium for my buffer solution will be hydrofluoric acid is in equilibrium with my hydrogen ion and my fluoride ion. Now I can go and make an ice chart and write a K expression and plug in my values and show my 5% rule and then calculate the pH from there, or I can use the Henderson-Hasselbalch equation, and that's much quicker to do. So pH equals pKa plus the log of my base over my acid. So if I take the negative log of my Ka value and add that to the log of my base over my acid, that'll give me my pH. So the pH of the solution is going to be 3.36. Okay, now let's look what happens when we add a strong base to our original buffer solution. So question number 2 says calculate the pH after 8.0 grams of sodium hydroxide is added to 2.50 liters of the above buffer solution. So I need to figure out what my reaction is going to be, and I know that if I have a strong acid or a strong base in a solution, it has to be a reactant. So the sodium hydroxide is going to be reacting with something in our buffer solution. And since sodium hydroxide is a base, it's going to be reacting with the acid component of my buffer solution, which is the hydrofluoric acid. Now I need to remember that when I take the sodium hydroxide and put it into water, it's a strong electrolyte. It's going to break up into sodium ions and hydroxide ions, and the sodium ions are spectator ions, so I'm not going to include them in my reaction. So I have my hydroxide ions, and I'm going to add them to my buffer solution. It's going to react with the acid in my buffer solution, which is the hydrofluoric acid. The hydrofluoric acid is going to donate a hydrogen ion to the hydroxide, so I'm going to produce water and fluoride ions. Notice that I have the arrow only going in one direction because strong acids and strong bases react to completion. Okay, so from there, I'm going to make a mole ice chart, and I'm going to react all of one of my reactants. It's a what word do I want to use? A limiting reactant problem. Okay, so when I do my calculations, 8.0 grams of sodium hydroxide equals 0.20 grams of sodium hydroxide. It's a 1-to-1 ratio of sodium hydroxide to hydroxide ions, so I have 0.20 moles of hydroxide ion. I'm going to take my molarity of my hydrofluoric acid and multiply it by my volume to get my moles of hydrofluoric acid. So 0.60 times 2.5 gives me 1.5 moles of hydrofluoric acid. I'm going to take the molarity times the volume of my potassium fluoride, and that'll give me the moles of my potassium fluoride. So 1.00 times 2.50 is going to give me 2.5 moles of potassium fluoride. It's a 1-to-1 ratio of potassium fluoride to fluoride ions, so I have 2.5 moles of fluoride ions. I'm going to plug those into my ice chart. All of my hydroxide will get consumed by my buffer solution. So I have 0.20 moles of hydroxide that's completely consumed. It's going to react with 0.20 moles of my hydrofluoric acid. That's going to leave me with 1.3 moles of hydrofluoric acid. And I'm going to produce 0.20 moles of fluoride ion, which is going to be added to the 2.5 moles that I started with. So I'm going to have 2.70 moles of fluoride ion when the reaction is complete. So I have an acid and a base left in my solution, so I still have my buffer solution. I can use my Henderson-Hasselbalch equation to calculate my pH. So pH equals my pKa plus my log of my base over my acid. So I'm going to get 3.46 for my pH. And notice that that makes sense because I added a strong base to my buffer solution. I would expect my pH to go up, even though it only goes up a little bit because I'm still within my buffer capacity. For the last problem, I want to calculate the pH after I add 0.40 moles of hydrochloric acid, which is a strong acid, to the solution in question number 2. So again, I'm going to be using a mole ice chart. I have 0.40 moles of my hydrochloric acid, which is a 1-to-1 ratio to hydrogen ion, so I have a 0.40 moles of hydrogen ion. From the problem above, I have 2.7 moles of fluoride ion and 1.3 moles of my hydrofluoric acid. Hydrochloric acid is a strong acid, so when I add it to my buffer solution, I know it's going to react with the base in my buffer solution, which is my fluoride ion. So my reaction is the hydrogen ion is going to react with the fluoride ion to produce hydrofluoric acid. All of my strong acid is going to react within my buffer capacity. So 0.40 moles of hydrogen ion are going to react with 0.40 moles of fluoride ion, and I'm going to produce 0.40 moles of hydrofluoric acid. So when the reaction is complete, I'm going to have 2.3 moles of fluoride ion and 1.7 moles of hydrofluoric acid left in my solution. And that is a weak acid and a base in the solution, so I still have my buffer solution intact. So I can use my Henderson-Hasselbalch equation again to calculate my pH. And now my pH is 3.27, which again makes sense because I added a strong acid to my buffer solution. I would expect my pH to be a little bit less than it was before, although there isn't a huge change because, again, buffer solutions resist changes in pH as long as we're within the buffer capacity. I will hopefully be back in school on Monday, and I plan on spending all of next week reviewing this chapter since I know that it's really hard. And on Monday, we will review buffers and we'll make a buffer solution and test the pH of that solution to make sure we're comfortable with how buffers work. I will see you then, and I hope this helped. Take care. Bye.